In this tutorial, we're going to talk about Newton's second law, also known as the law of acceleration. For the learning target, we're specifically going to focus on the statement of the second law, including the equation, and then, of course, the application of this concept in real-life scenarios. So first, let's have a recall. For the law of inertia, or Newton's first law, the law basically describes how objects behave when the net force is zero. Now, for the second law, or law of acceleration, what it does as a law is it describes how objects behave when the net force is not zero. So what exactly does it say? For the general statement, the second law of motion simply says that if a net external force acts on a body, the body accelerates. And then take note that the direction of acceleration is the same as the direction of the net force. It also says here that the mass of the body times the acceleration vector equals the net force vector. And that looks like this in equation form. So take note that in equation form, sigma F equals ma, the letter m represents mass, or the mass of the body that you are dealing with or analyzing in your problem or in your situation. And then sigma F is the summation of forces, or the net external force acting on a body, and then acceleration is the acceleration that will be experienced by the mass that you're dealing with as a result of the net external force acting on it. So that is that simple. But before we delve deeper into that, I want you to try answering this physics puzzler. You can do that mentally, or maybe write down your guess, your educated guess. And the question here is, racing motorcycles, they're pretty cool, right? They travel really fast, aside from the fact that they look so slick. And my question is, how can you apply Newton's second law in designing a high-performance motorcycle? Of course, there are points to consider in designing a racing motorcycle. They don't perform just like ordinary motorcycles. They are specially designed to be used for racing purposes. And as a hint, of course, the second law of motion equation is the only hint that I'm going to give at this point, which states that net external force equals mass times the acceleration vector. So that's it. You can take a guess, but at this point, we're gonna delve deeper into the Newton's second law. Okay, so first let's talk about the units. So we have the SI units, the CGS units, and the British units. Most probably, you're gonna encounter the SI unit in most physics problems, so this is what you have to remember the most. But just so you are aware and you don't get shocked when you look at other references or specific physics problems, I'm showing you the other units for familiarity. And then, take note as well that when you say 1 Newton in physics, it is defined as the force needed or required to accelerate a 1 kilogram mass at a rate of 1 meter per second squared. That's why if you look at this, because sigma F equals ma, if you think about the equation, multiplying mass and acceleration will lead you to kilogram meters per second squared. So technically or mathematically, 1 Newton is equivalent to kilogram meters per second squared. So what, miss, do we have to remember that? Yeah, definitely, you have to remember that 1 Newton is equivalent to kilogram meters per second squared, because when you do problem solving, you will not be able to properly cancel the units if you don't know that 1 Newton is equivalent to kilogram meters per second squared. So that's one important point. But in case you're wondering, miss, I'm curious. I know that Newton is a unit of force. So how strong is 1 Newton? Just for visualization, imagine a medium-sized apple. Miss, why? Is it your favorite fruit? Yeah, that's one. But there's another reason why. Like, if you put a medium-sized apple on the palm of your hand, that force you're feeling, or the weight of the apple that you're feeling or sensing against your palm, is actually how strong 1 Newton is. Okay, or approximately, that's how 1 Newton feels. Also, for the other units, your teacher might give you the equivalent or the conversion factors between Newton and dyne, for example. But for this slide, I did not include that in case your teacher asks you to memorize that, and you're gonna have to do so. Next, going further with the second law equation, so again, that's sigma F, or summation of forces equals mass times acceleration. But to expound this further, take note that it's important to remember that the forces we're talking about in this equation are just the external force or forces acting on a body. When you say external, of course, it should be something that is not provided by the mass itself that you are dealing with. So this mass accelerates as a result of the external forces acting on it. So just to give that a bit more sense, just imagine you're wearing a belt. if you try to lift yourself up, like towards the ceiling, by pulling your own belt, definitely by common sense, you're not gonna accelerate. You cannot lift yourself towards the ceiling by pulling your own belt up. Because according to Newton's second law, only external forces can affect the acceleration of a certain mass or a certain object. Miss, how do you visualize a net external force? Or if I'm wearing a belt, how would a net external force be like if it's not me pulling myself? Well, definitely, if the own force is exerted by the body itself, like your hand, pulling the belt up, and the hand is, of course, part of your body. So that's an internal force in the entire human belt system, right? So for you to have an external force, you can do something like this. So it's a clip from a movie called So Close. It's a 2002 action film. So if you want to like be lifted up using your belt, it should look something like this. Okay, so as you can see, that's a belt with a retractable cord or cable. And what it basically did is, so the cable basically clings itself around this railing, and then that allowed this assassin to like get lifted because of course the railing provides an external support that is not part of this woman's body. And in that case, when the cable is supported by that external railing, then the cable therefore can exert an upward force or an external tension force that enables it to like lift this woman upward. So let's watch that again. But of course, take note, no matter how strong the cable is, if the woman herself is the one who pulls it upward, definitely she's not gonna accelerate. So again, it has to be a net external force to like make something accelerate. Going forward, remember as well that M is the mass of the body in this equation. So in that case, then the mass would be the woman. And then again, the net external force is provided by the cable, lifting it upward with the help of the railing as a support force. And then take note as well that the mass must be constant in the second law equation. So example, if the problem is about a leaking tank truck or a rocket ship, because a rocket ship's mass is definitely not constant, it's losing its fuel throughout the entire trip. And when you have cases like this, they are better handled by using momentum concepts that we're going to be dealing with in a separate lesson. Okay? So also take note that just like the first law of motion or law of inertia, the second law is valid in inertial frames of reference only. And if you don't remember what inertial frames of reference are, these are these are frames that are either at rest or moving at constant velocity. No rotation, etc. No acceleration. That's it. And the acceleration in this equation is always in the same direction as the net force. So say for example, you have a soccer ball. The soccer ball is at rest. This is a very easy concept to explain. So if you exert a net force on the soccer ball, of course, by common sense, you know that this ball will accelerate rightward. And then if you have a leftward force exerted on the soccer ball, which is at rest, then obviously the soccer will accelerate leftward. So pretty easy, miss. Okay, well, now let's talk about objects in motion. In this table, what I basically did is I summarized the consequences of net force acting in certain directions with respect to the initial direction of motion. Because sometimes I'm trying to avoid students having this misconception that for them to understand where the acceleration is going or where the acceleration is directed, they're looking at the motion of the object. So sometimes they associate the fact that, oh, if the object is going leftward, the acceleration is leftward. No, not necessarily. I'm going to show you specific cases in the next slides. But for this particular slide, I'd like to emphasize one key point, which is this. It says here that the acceleration of an object is in the same direction as the net force acting on it. So as you can see in the middle column, I wrote here the direction of the net force and acceleration for specific cases. And as you can see, I did not put the direction of net force and acceleration in separate columns because their directions are always the same. So if the net force is rightward, and so is the acceleration. If the net force acting on an object is leftward, then the object's acceleration would be leftward. And take note that these directions are not necessarily referring to the object's direction of motion, okay? Acceleration or net force do not necessarily define or tell you where the object is going, okay? But they tell you the consequences of this net force depending on where the object is initially going. And that's what we're going to look at in the next slide. So in here, it says here that if the net force points in the same direction as the initial motion, the object speeds up. To visualize that, okay, so imagine this is an icy surface. And then there is a hockey puck, okay? So that's a huge hockey puck. Now, this hockey puck is going rightward. So there, it's moving like that. So if you exert a net force on it that is also pointed rightward. Let's say, for example, you push it further with your hands. Because in this case, it's just sliding in an icy surface by its own inertia. It's moving at a constant velocity, let's say. But then, yeah, you exerted a net force all of a sudden. Okay, let's say it's an experiment. What will happen is that the object will speed up. Of course, by common sense or like, I don't know, general knowledge, maybe you would know it will speed up if you push it in the same direction as its motion, right? And yeah, that's actually true. In physics, it's also correct because if you exert a net external force in the same direction where the object is already going, you're reinforcing the momentum that is already present in that object. So rightward momentum, and then you exerted a rightward net force, you would expect the object to speed up. So that's the point of that. Next. Going forward, if the object is going leftward and then you exert a leftward net force on it, then what will happen is that the object will speed up again, okay? So always remember what you have to take note in here is that if the initial direction of motion of an object or the original motion is in the same direction as the net force exerted on it, then that object will speed up, okay? So that's it. You can see that in the first and the fourth row of this table. Next, for key point number 3, if the net force opposes the initial direction of motion, the object slows down. And by common knowledge or by just general perception and experience, of course, we know this, okay? Which makes sense because you are opposing its motion. So what will happen is that the momentum you're giving the object will basically cancel its original momentum. So it makes sense that it will slow down. So if the object is originally moving in a rightward direction at constant velocity, exerting a leftward net force on it will obviously cause it to slow down. And then if the object is going leftward originally, so what will happen is that if you exert a rightward force on it, you're opposing its momentum. So what will happen is that it will slow down, okay? So take note, what I want you to notice, like what I said earlier, is that the direction of the net force, which is also the direction of the acceleration, does not necessarily tell you where the object is going. So example, you might read a problem and it's describing, oh, there's a net force acting on an object and it's this net force or acceleration is pointing rightward. It doesn't mean that the object is going rightward, okay? That's an important point. So in this case, there's a rightward net force and rightward acceleration, therefore, acting on the object, but the object is going leftward. So yeah, you see the point, the acceleration, please avoid the misconception that the direction of the net force and acceleration will automatically tell you the direction of the object's motion. Because in this case, no, it's going leftward and you have a rightward acceleration, but the object is still going leftward, right? It just slows down. Now take note, apart from slowing down, the object may also eventually come to a stop depending on how long the force is acting as well as the overall magnitude of the force. Okay? So net external forces do not only speed up or slow down something, but it's also capable of making something completely come to a stop or make something move out of being at rest. Okay, so that's it. Going forward, for objects that are moving in a circular or curved path, example, planets orbiting a star, or example, our amazing natural satellite moon. As the satellite of the planet Earth, what the moon is basically doing is it's moving in an orbit around our planet Earth. And then when that is the case, the acceleration of that object, of that satellite, is pointing towards the center of the circle. And that is what we call a centripetal force in physics, or what also called as the center-seeking force. What the planet Earth basically does is as a result of its gravity, it exerts a net external force on the moon directed towards its center. And that is the reason why the linear velocity of the moon or whatever satellite is constantly changing, and that allows it to follow an orbit. Next point, take note that the acceleration of an object is directly proportional to the net force acting on it. So in this part, we're gonna relate force and acceleration, which is pretty simple. If you look at the equation, you can actually see that the acceleration and net force have a direct relationship, meaning to say, when the force is increased or when the net force is increased, the acceleration will also increase. So if you have two identical balls in here, they have the same masses. If you exert a certain amount of force to this mass, of course, it will accelerate at a certain value, which we will call as A. But if you exert twice the amount of force on the ball with the same mass, what will happen with the acceleration is it will be doubled, okay? So twice the net force, then twice the acceleration. That's what you mean by direct relationship. And that applies when when you are comparing two identical masses, okay? So remember those concepts because sometimes you might encounter physics exam questions where they would ask you, if you double or if you triple the net force acting on an object, what will happen to the acceleration? Letter A, will it be doubled, etc. Something like that. So that's just an exam tip. And then second point I like to make, while force and acceleration have direct relation, for mass and acceleration is actually an inverse relationship. So for mass and acceleration, what we have is an inverse relationship, and you can see that in the equation. So acceleration is inversely proportional to the mass of an object, meaning to say, for a certain value of net force, more mass means less acceleration, and less mass would mean more acceleration, which makes sense because in everyday life, of course, we have experienced that something that is more massive is harder to accelerate if you give it a certain amount of force. So this equation really makes sense. And that's why you shouldn't be intimidated with equations, because these equations are nothing but just, mathematical representations of the concepts that we actually experience in everyday life. So going forward, to visualize that further, if you have a light tennis ball and a basketball, for example, then the basketball, being more massive compared to the tennis ball, if you give them the net external force equal to 3 newtons, for example, or if you give them the same value or magnitude of net external force, the one with the less mass, the tennis ball, compared to the one with the greater mass, will experience greater acceleration. Basketballs are... I'm not talking about the sport, I'm talking about balls. So basketballs are more massive compared to baseballs. That's why if you watch like baseball games like this, it's quite common to like see baseballs flying off like towards the audience, right? And even the ones that are far away from the field, they actually get hit by a baseball. But you don't get to see the same thing happening in basketball events because number one, basketballs are more massive than baseballs. And second point, of course, is also because of the way that the basketball is played around when they're in the court. Usually they just try to aim it towards the ring. That's also the reason why. Yeah, but overall, compared to basketballs, baseballs are more likely to fly towards the audience, while basketballs, if ever they hit some people in the audience, probably just the ones in the front sections of the rows or the seats, right? So that's it. So this makes sense. Okay, so again, mass and acceleration are inversely proportional for a certain amount of force. Going forward, take note also that experiments show that the net force on a body is what causes the body to accelerate. When you say net force, it's the sum of the forces acting on an object. So meaning to say, if there are multiple or several forces acting on the same body at the same time, then the acceleration of that object will depend on the vector sum of all those forces acting. So in this case, the acceleration of the rope will depend on the vector sum of the individual forces exerted by these men on the rope. If the forces collectively exerted rightward are greater than the sum of the leftward forces, then the rope will accelerate to the right. Okay, going back to our physics puzzler. So again, how can you apply Newton's second law in designing a high-performance motorcycle? So it can be tricky at first, especially because I gave you this equation as a hint, but I wrote it this way. So when you're asked a question like this, the question is conceptual, and you are looking at this equation as a hint, you can ask yourself first, if I were to design a high-performance motorcycle, what variable is it that will tell you, oh, this motorcycle is doing great? Of course, that would be acceleration. Because a high-performance motorcycle should be able to accelerate at great speeds from 0 meters per second going to a really massive speed for it to perform really well. Apart from that, it should also be able to stop as effectively as possible. So it's the acceleration that we actually want to manipulate. Therefore, this is not the best way to like write this equation if you want it to help you answer this conceptual question. And I'd rather write it this way. So if you look at this equation, it actually clearly tells you that If you want a very high acceleration for your high-performance motorcycle, you would want the mass of your motorcycle to be as low as possible because acceleration and mass are inversely related. So lower mass means higher acceleration for the motorcycle. Of course, you cannot control how heavy the driver will be, right? But you can control the mass of your motorcycle. Apart from that, this equation also shows that the higher the net force is, the higher the acceleration will be. So net force and acceleration are directly proportional. Meaning to say, what we want this high-performance motorcycle to be is we want it to be designed to achieve the maximum acceleration by reducing its mass. So again, lower mass, more acceleration. And then we're gonna equip it with a really powerful engine to generate a great forward force. Because if you maximize the net force acting on this motorcycle, basically the way the engine is propelling it forward, then you're gonna have a very high acceleration. So again, it's a matter of manipulating the variables that we can control for us to achieve the target acceleration that we are aiming for. And to make that happen, of course, for mass, typically they just use lightweight metals like titanium, for example. And for the powerful engine, they normally use engines with cylinders that can hold more fuel and air because that would mean greater power output and therefore more forward force. So that's it for this physics puzzler. So again, whenever you encounter a question like this, go back to the principle that you're asked to use. So if it says Newton's second law, think about the equation. Think about the variables you want to control or you want to target, and then look at the variables that can possibly be manipulated so that you can come up with a conceptual answer like this. So that's it. Next, for our concept check, a coin was dropped from rest from a tower. If air resistance is negligible, how does the net force on the coin vary as it falls? Well, okay, so first thing you have to remember, if you have a coin and it's dropped from a certain height, it's actually in a state of free fall, right? Because it says here, air resistance is negligible. So if you can neglect air resistance, definitely this object is in free fall. It's a freely falling body, meaning to say, only the Earth's gravity is affecting its motion. Okay? And take note, if only gravity is affecting this object's motion, since air resistance is negligible, it means that this coin would be accelerating at negative 9.8 meters per second squared. And when that is the case, if you go back to the equation, it shows you that for a certain mass, let's say the coin, if the acceleration has a certain value and it's constant throughout the object's motion, then the net force must also be constant, right? Because if you vary the net force for a constant mass, then the acceleration would also vary. But knowing the fact that the acceleration of the object is constant, it would also tell us that the net force acting on the object, or the coin, is also constant. So again, since the coin is in free fall, its acceleration is constant at 9.8 meters per second squared, and therefore, if acceleration is constant, then the net force acting on it is also constant. So again, the net force on the coin will not vary. It's gonna stay the same throughout its entire trip. Anyway, it's actually equal to its own weight because weight is basically the amount of force that gravity is exerting on the objects around it. So that's it. And for the summary of key concepts, there we have them. You can copy them or take a screenshot of this slide. And that's all for this video. I hope that this has been helpful. Thank you so much for watching.